Hello, everyone. For today's lecture, we will be discussing bonding and Lewis structures. We're first going to start with chapter 3 of the textbook, which is focused on ionic bonding. Before we talk about ionic bonding, though, we need to understand noble gases and their electron configuration. Noble gases are the last group in the periodic table. They can be found all the way to the right, and they all have one thing in common, which is that their outer energy shell or their valence energy shell has a full electron configuration. Let's look at helium as an example. So helium has one energy shell, and as we discussed in our last lecture, that energy shell has an s orbital that can hold 2 electrons. And so we can see in this electron configuration that the 1s orbital is full with its 2 electrons. And the same trend can be found in the following noble gases here. So for neon, using a shortened electron configuration, we can focus on the second energy shell, which has the s orbital and p orbital, and the s orbital is full with its 2 electrons, and the p orbitals are full with 6 electrons, which is a total of 8. So this trend can be found throughout the rest of the noble gases. We can see here for argon, krypton, xenon, and radon that they share this configuration of their outer energy shell here, having an s2 electron configuration and a p6. And you can see this for xenon, S2, P6, and radon, S2, P6. And we call this a noble gas configuration. And because these gases have the last energy shell being completely full of electrons, these gases are stable, and they're called noble gases because they don't bond or interact with any other molecule, and they're stable and happy. So that is why other atoms on the periodic table do form bonds. They form bonds so that they can achieve this stable state and have an electron configuration that looks like these noble gases here. So, as we stated, bonding occurs in order for each atom or group of atoms to achieve noble gas configuration. And a shorthand of this is having N, where N equals the energy shell, S, the s orbital, and 2 is the amount of electrons in that orbital. N, again, is this energy shell. P is the orbital, and it will be full with 6. And all atoms in the periodic table that aren't noble gases would like to achieve this configuration. There are 2 types of bonding. Ionic bonding, which involves the exchange of electrons, resulting in each atom achieving a noble gas configuration. And then there's also covalent bonding, which involves the sharing of electrons, resulting in each atom achieving noble gas configuration. So again, to point out the difference, in ionic bonding, we are exchanging, so either gaining or losing electrons. And in covalent bonding, we are not gaining or losing, but we're actually sharing those electrons. So when does each of these happen? The deciding factor is the electronegativity of each atom. And in the last lecture, we talked about electronegativity, which is the ability to take electrons on if you're an atom. And atoms with high electronegativity have the ability to take electrons from atoms with low electronegativity. And we know that there are trends on the periodic table that we can follow to figure out whether one atom is more or less electronegative than the other. This usually happens between a metal and a nonmetal. Atoms with a smaller difference between their electronegativities will be more likely to share electrons. And this is when covalent bonding happens. And this usually happens between 2 nonmetals. So here's a visual representation of each type of bonding, and we will dive further into these concepts. But on the left, we're showing covalent bonding, where we have 2 atoms, and they have the same electronegativity. So here, when these atoms come together, they're going to share these electrons in the middle so that they have a noble gas configuration, and it's the sharing of these electrons that forms the bond. On the right, we're showing ionic bonding. So here we have 2 atoms, and one is more electronegative than the other. So the atom here on the left is less electronegative than the atom here on the right. So the atom on the right is actually going to take those electrons from the atom on the left. And when you take those electrons, you form a negative ion, and then the atom that gave those electrons up becomes positive. And because positive and negatives attract, you form a bond in the middle of those two. So we are going to, in the next few slides, dive deeply into ionic bonding and what ions are. Ions are atoms or groups of atoms that contain more or fewer electrons than protons. Cations are a result of the loss of one or more electrons, and anions are the result of the gain of one or more electrons. And these cations and anions have a charge. If you use these simple equations here, if you have an atom that has more protons than electrons, then you're going to have a positive charge. Remember, protons have a positive charge, electrons have a negative charge. So if you have more protons, then you're going to be more positive, and that is what we call a cation. If you have more electrons than you have protons, because electrons have a negative charge, then the overall atom is going to have a negative charge, and this is what we call an anion. So here is just what we would use as an equation for the formation of an anion. Let's say that we have this atom here, chlorine, and if it's a neutral chlorine, and we can find this out from the periodic table, we have 17 protons and 17 electrons. So everything's equal, there's no charge. But let's say that chlorine molecule actually gains an electron. Therefore, we have more electrons, now 18 electrons and 17 protons. And because we have more electrons than we do protons, we're going to have this negative charge here on the chlorine atom, and this is going to form a chlorine anion. Now, let's look at the formation of a cation. Again, we'll start with a neutral sodium atom. And then if we lose an electron, so we'll see here that in this equation, we have that the electron is not being gained, but it's on the product side where we're actually losing this electron. And because we lost the electron, meaning we have more protons than we do more protons than we do electrons, we're going to have this positive charge here, and then the electron that we lost separately. And this is going to be forming a sodium cation. And you can lose more than one electron, and you can also gain more than one electron as well. So we'll have this example here that we have calcium. And if we lose the electron, so that means that we're going to have these electrons independently here on the product side. We now have more protons, 2 more protons than we do electrons in this atom. And so we're going to have a calcium cation that has a 2+ charge. So we look at the periodic table, we can kind of tell which ions are going to be made by their position in the periodic table. Groups are the columns that are on the periodic table, and group 1 forms these +1 ions. These are lithium, sodium, potassium. Group 2 form +2 ions, so this is beryllium, magnesium, calcium. Group 3 forms +3 ions, so this is aluminum. Group 6 form -2 ions, so we have oxygen and sulfur. And then we have group 7, and these form a -1 ion. So fluorine, chlorine, bromine, and iodine. And it's just particularly easy here for these groups because group 1, 2, and 3 kind of correspond with the ions that they're going to form. And what do all these ions have in common? Well, if you have lithium and you take one electron away, now it looks like its closest noble gas on the periodic table. And so that would give it a noble gas configuration of NS2 and NP6. And notice that um, the metals will form cations, so they tend to um, lose their electrons, and the nonmetals form anions, meaning they tend to take on electrons. So we're going to look at the periodic table here. All the metals are shown here in the blue. We have these metalloids here that are on the green, and we have our nonmetals here on that are in this beige color. And with the exception of hydrogen, most of the nonmetals are on the left side of the periodic table, and most of the metals, nonmetals, are here on our left side. So if we look at lithium, for example, it is going to lose an electron. So we said that it's in group 1, so it tends to form a lithium +1 cation. And the reason why it does that is because if it loses that electron, now it has the electron configuration of helium, which on the first slide we showed is a noble gas. And that is true of all of these in this group 1. Sodium will form a +1 cation, and if it loses that electron, it's going to now look like neon. It's going to have the electron configuration of neon, which will make it stable and look like a noble gas. And we can do the same thing for fluorine, which has a -1 anion. So if it gains an electron, it now looks like neon. It looks like its closest electron, noble gas. And the same to be true of oxygen, which has a -2 anion. If it gains 2 electrons, it now looks like neon. So this is just to highlight that this either loss or gain is so that it can look like its closest noble gas. So we have 2 different ions that can form. We can have monoatomic ions, and this contains only one atom. So this is like sodium, chlorine, calcium, oxygen. You can see here there's only one atom here. Conversely, we have polyatomic ions, and these contain more than one atom. So this is a hydroxide ion, and so it has oxygen and hydrogen that have this negative charge on it. And so this charge applies to this entire ion, poly meaning more than one here. So it's not just the oxygen with the minus, it's not just the hydrogen, it's this OH molecule that has this charge. So here's a list of some common polyatomic ions that you might see. You will not need to remember these. If you do need to know them, you will have a table, but this is just to show ammonium. We have an acetate ion, carbonate, and here's their their name. So also we have some cations here. So ammonium is a cation because it has a positive charge, and then these are anions here. So ionic compounds form when 2 ions are attracted to each other due to their electrostatic forces. So what we did in the last couple of slides is we talked about what ions are and how they form. And now we're going to talk about how those ions actually form, are utilized to make compounds. So what we showed is that because positive and negatives attract each other, there's actually going to be this bond that's formed in the middle. So let's take sodium chloride, which is known as table salt, as an example. Sodium has a plus charge, a +1 charge, so it's a cation. And we have chlorine that has a -1 charge, that is an anion. And because positives and negatives attract, they form this sodium chloride or NaCl molecule, and it is neutral. So that means that the positive charge and the negative charge balance each other. Let's look at a bond that's formed between our polyatomic ions. So magnesium is in that second group. It's going to have a 2+ cation. And then we learned about polyatomic. This is hydroxide. It has a -1 anion. So the problem here is that if we just put these together, they're not going to be a neutral charge. In order to do that, though, we need to have two hydroxide anions, so that will have a -2 to balance out that magnesium 2+ charge. And the resulting compound is neutral, and this is known as an ionic bond. It's those positive and negatives coming together to form that bond. So let's look at this as a visual representation here, where we are actually going to have one ion lose while the other ion gains. So we're going back to our example of sodium chloride, where we have a sodium molecule and a chlorine molecule. This sodium is actually going to give its electron to chlorine. When it gives that electron to chlorine, you'll see here that this independent electron is gone. And so this sodium is going to lose, no longer have an electron in that last energy shell. So here where we have 1, 2, 3, now we just have 2 energy shells, but that energy shell is now full. Sodium is happy and it has that positive charge on it. Now, if we look at chlorine, chlorine has 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell, and it's going to gain that 1 electron here. And now it's going to have a full energy shell, 1, 2, 3, third energy shell, and a negative charge. So these atoms are now looking like the nearest noble gas. They have a noble gas electron configuration, they're stable. And because of that positive charge and that negative charge, they're now going to be attracted to each other and form a bond. And that bond is going to form the molecule sodium chloride. So this is an example of some common ionic compounds. This is calcium chloride here. So because we have a +2 charge and a -1, we're actually going to need 2 of these chlorine anions to form a neutral compound. So in the next slide, we're going to go through how we kind of come to that conclusion, but these are some common compounds and their cation and anions and the compounds that they form. So how do we get to the chemical formula? What we're going to do very easily is exchange the superscripts to generate the subscripts. So superscripts are these numbers that are at the top, and subscripts are the numbers that are at the bottom. So when we look at magnesium bromide, we're going to see that magnesium is in that second group. It's going to have a 2+ cation, and bromine is going to have a -1 anion. And because we want our resulting compound to be neutral, we're going to need more than one bromide. And so a simple way to figure this out is you take this superscript here, so superscript up top, and you bring it down to the bottom to magnesium. And then you're going to take the superscript that's on magnesium and bring it down to the bottom of bromine. And the resulting compound is magnesium bromide, which is going to be 1 magnesium because we took that 1 down here, and 2 bromine atoms because we took that 2 down here. Let's look at aluminum oxide. So we're going to do the same thing. Aluminum is a 3+ cation, and oxygen is a 2- anion. So you might think you have to do some fancy math to kind of balance out these charges, but you don't. All you have to do is take the superscript that's at the top and bring it down to the bottom of this atom here, and then bring the superscript that's at the top and bring this down to the atom here. So when we do that, we get aluminum 2 aluminum atoms. So the superscripts tell you how many atoms are in that molecule. So because we have the 2 here and we bring it down to the aluminum, that brings us to 2. And because we're going to take this 3 plus and bring it down here to the oxygen, that gives us 3. And the resulting molecules or resulting compounds are now neutral. So how about you take some time and do some practice? You can pause the video here and do the same thing. Take this positive charge, bring it down, and take this negative charge and bring this down. When you bring the superscripts down, you don't actually have to bring the charge because we are making a neutral atom. So you can pretend there is a 1 here, bring that down. There's a 2 here, bring that down. So take a few minutes, pause the video, and make the compounds for each of these cations and anionic pairs. So if you took some time, these are what your answers should look like. Once you bring that 1 charge and that 2 charge over, you get sodium oxide, where you have 2 sodium atoms and then 1 oxygen atom. Magnesium sulfide has 1 and 1, and you can continue to do the rest here. So how do we name these ionic compounds? It's really simple. Ionic compounds fall into 2 categories: group 1 or 2 metals with a non-metal, and then you can have a transition metal. So the transition metals are in the middle, exact middle of the periodic table with the non-metal. Group 1 or 2 metals with a non-metal are very easy to name. How you're going to do is take the metal name and then the non-metal name and put "ide" at the end. So some of the compounds that we saw in the previous slide, we can drop the ending of the non-metal before adding the "ide." So we have sodium and chlorine, and they're going to form sodium, which is the metal name, and then chloride, which is the non-metal name, and "ide" at the end. For calcium and a fluorine, you have calcium fluoride. For barium and oxygen, we form barium oxide. And then for magnesium and nitrogen, we form magnesium nitride. For transition metals, compounds, we have some different naming. So transition metals can have multiple charges due to the fact that they often cannot achieve noble gas configuration. So they choose to have a half-filled or filled D subshell with no electrons in the S subshell. And this can be a little bit more complicated. We won't be doing much with these transition metals, but I do want you to have an understanding of how to name them. So a filled S subshell and no you can have a few combinations, since the transition metals often don't achieve a noble gas configuration. So you can have a half filled or filled D shell with no electrons in the S shell, as I mentioned previously. You can have a filled S subshell and no electrons in the D subshell. And then you can have half filled S and D subshells. So because of this, we need to identify the charge on the transition metal, and we do so using a Roman numeral in parentheses after the name of the transition metal. So these compounds will have in essence the same name. They both will be iron chloride. But because in this molecule, the iron has a +2 charge, we're going to indicate that by putting 2 in these parentheses in between iron and chloride. And because here, this iron chloride has a +3 anion, cation, we indicate that by putting 3 here. So now we're going to talk about naming polyatomic ion compounds. These are ionic compounds that contain polyatomic ions, and you do this by simply using the name of the polyatomic ion and then in the name. So here is this cation ammonium. It has a +1 charge, and to name this, we use a very similar naming to what we use for other metal and non-metal combinations. So we use ammonium and then chloride. So we still take that chlorine and add IDE to the end. For barium carbonate, carbonate is this entire CO3 here. So we include that in the name. For potassium sulfate, it's this polyatomic sulfate here. And then we can have ammonium sulfate. So this is actually a combination of two polyatomic ions where ammonium has this charge and the phosphate has this charge. It forms one neutral atom, which is ammonium sulfate. So we use both of those polyatomic names here. So that's going to sum up what we know about ionic compounds. We'll do some more practice in our in-class portion of the lecture, but now we're going to move on to chapter 4 of the textbook, where we will talk about covalent compounds. So we talked about in the previous chapter how salts form, or compounds that are formed between a metal and a non-metal form this ionic bond. And I apologize here, these